So once again, welcome to all the participants for the day 5 session 1. So today we will mostly focusing on implementation of artificial neural networks or feed forward neural network in Python and also in the MATLAB. So actually, do you think machine learning approach using ANN or deep learning approach using deep neural networks is required to estimate the or to predict the roots of a quadratic equation? Hope my voice is audible. So my question is the implementation of ANN or implementation of DNN is required to predict the or to estimate the or to calculate the roots of a quadratic equation?
No.
No, it's not required, because if you want to find the roots of a quadratic equation, we have a deterministic approach. That means if you know the coefficients, we can calculate the roots by using the deterministic approach with a deterministic formula that is called minus b plus or minus root of b square minus of or is about 2a, right? So for such cases, no need of machine learning, all those things, because we have a specific a deterministic equation, some mathematical formula. So then where we can use? So actually machine learning or deep learning using ANN or deep neural networks, whatever it may be, is required to predict some variable based on some input features if there is no proper mathematical relation between the two. If there is no proper mathematical relation exist between your input features and your output variable is not available, then you go with machine learning approach or deep learning approach. If you have a proper deterministic mathematical relation is exist between input feature and your output variable, which you are going to predict. If it is available, then no need to go for all these stuff. So writing the code, mathematical analysis, tuning the hyperparameters, these all things are not required, because we have a proper formula, we have a proper mathematical relation. But most of the problems in our real time, we don't have a fair mathematical relation between the input features and output variable. In such scenario, we are using the machine learning and deep learning. So we are using the ANN or deep neural networks. So what this will do, what this machine learning approach or deep learning approach or ANN or DNN, what it will do? It will do, it will trying to establish, a nonlinear mathematical relation. It's trying to establish a nonlinear complex mathematical relation between your input features and your output variable. It will build that relation. So that's what we are doing. So we are trying to build an appropriate we are trying to build an appropriate nonlinear complex relation between the input features x1, x2, x3 and your output variable y by using different type of activation functions, by using different type of hidden layers, by using different number of hidden neurons. For all these things, we are tuning to build some mathematical relation between your output variable and input variable, so that if you give some input variables, your model able to predict an appropriate output, a good output, an accurate output. Hope you understand what the machine learning deep learning is doing. Just it is trying to build some nonlinear mathematical relation between the input features and output variable where already not exist. There is no relation exist between the input features and output variable. Now our machine learning models or deep learning models, ANN or DNN, it will try to build some mathematical relation between your output variable and input features. When we discussed in the last class, so if you coming to recollect what we discussed in the last class, so two models we discussed in the last class. One model with only weights and another model with only with weights and bias parameters. Then what that ANN model is doing, it trying to build some relation between your output variable in terms of your input variable and weights and the bias parameters. Actually, there is no proper relation between the y and x. Now, based on the data which I am giving, x and y values, then it is trying to update the weights and bias values so that it try to build some an appropriate mathematical relation between your x and y, your input features and the output variable. So that's what we are doing in the last class and what we discussed till now. Just we are trying to build some relation between your input features and the output feature based on your model parameters, weights and bias parameters. Of course, our problem in real-time problems are the highly nonlinear, highly complex. So this type of linear relation will not exist. If your ANN is capable to build some linear relation between the input features and output feature, then it won't work. It will not good at all in the real time. Because in the real time, so most of the applications, most of the problems are the highly nonlinear. So we have to concentrate on some complex nonlinear relation between your input and output features. Hope you understand. So now how we increase the complexity of the relation? How we increase the complexity of the relation, or how we extract the complex relation between your input features and the output variable? That can be done by increasing the hidden layers and by increasing the hidden neurons based on the requirement. So don't feel that if you increase the hidden layers continuously, if you increase the hidden neurons continuously, we will get the good model, that model predict well. No, no. That is depending upon the data. For example, I'm telling, suppose one LKG student joined in a classroom. I want to make good knowledge to him. If I explain a trigonometry to him, it's not use. Hope you understand what I'm telling. One LKG student joined in a class. I am an expert in the mathematics. I want to give good knowledge to this LKG student. Then I start teaching trigonometry. What is the use? No. So you have to make him learn what he is able to, what he is capable. Similarly, you have to build the ANN model based on your problem, based on your data. Okay, so like that you have to. That's why if you have a particular data, if you have a very complex model which works well in some other data, so that won't fit for this one. So you have to change the parameters, you have to change the neurons, you have to change the hidden layers. So don't think that a complex model always give the good result in all the cases. No. If your data relation is highly linear, if you give your nonlinear ANN model, it won't work. So that's depending upon the your data. So based on the data, you have to train your models and everything. You have to tune the parameters every time. So that's why most of the problems in the real time are the nonlinear in nature. So uh, we have to build some complex relation and nonlinear relation between the your input features and the output variable. So first, I want to build the complex relation. I want to increase the complexity of the model. I want to increase the complex relation between the input features and output features. And later we will add the nonlinear also. So how we increase the complexity? So let's assume in the previous case, let's assume we have the three features x1, x2, and x3. So because I have the three features, I have the three neurons in the input layer x1, x2, x3. I have the three neurons in the input layer. Okay. And in the last class, we discussed about the only one output neuron because I'm going to predict only one variable. So that is called YP, where Y is called as your actual output. For x1, x2, and x3, this is the input features. Your Y is the actual output, where YP is the predicted value. So in the previous case, we are not using any hidden layer, but ANN without hidden layer, it won't work in the real time. So you have to increase the complexity of the model. So how we can increase the complexity of the model? Just I am trying to add the hidden layers. So you no need to be, you can add one layer, two layer, or three layer. If you increase the number of layers, it's called as a deep neural network. If it is a single 1 to 2, so 1 to 2 layers, then it comes under the machine learning, a shallow network. If it is more hidden layer, it's called as a deep network, deep neural network. So just I'm trying to explain with only single layer as of now. So explanation with multiple hidden layers somewhat difficult. So we can, but if you understand this one, you are able to visualize the remaining part also. That's not a good deal. That's not a difficult, much difficult. But you can, if you understand this approach, you can do it for any number of layers. Same thing will be happening there also. So this is called as input layer, which contains the number of neurons that's equal to 3 because we have the number of features 3. And this is your output layer. You have only one output variable. So you have the only output, one output neuron. And whereas in the hidden layer, so the number of hidden layers and the number of neurons in each hidden layer are random in nature. So there is no thumb rule. So you have to keep these number of hidden layers only. You have to keep these number of hidden neurons only. No. So you have to try with various combinations. Maybe in one article I tried, initially I set up only one layer and increase the number of hidden neurons. So input layer is mandatory, output layer is mandatory, and I set only one hidden layer. This is called as the hidden layer. I will represent the hidden layer with J. I will represent input layer with I, and I represent the output layer with K. So here I am using only one hidden layer. So in my articles, what I write initially, I kept only one hidden layer initially, and increasing the neurons or varying the neurons and observing the performance of the model. So at a particular number of hidden neurons, if my model performing well, then I keeping that neurons in the hidden layer fixed, and I try to increase the layers continuously, and again executing the code and evaluating the model again and again, and I'm observing the error, and which gives the best result. I will keep that model for my deployment in the application. So hope you understand what I meant to say. So in this case study, to explain you, I considered one input layer which contains the 3 neurons because the 3 input features. I consider the one output layer with 1 neuron because I had the 1 output feature. Whereas the number of neurons in the hidden layer, I considered the 5. No need to stick for the 5 only. Just only for the explanation purpose, I consider the 5. So you can choose any. So you have to verify your performance of the model. Fine. And as the human brain, all the neurons are interconnected. So all the neurons are interconnected like this. So similarly, all the neurons are interconnected, and input neurons, each input neuron connected to the each hidden neuron, and similarly, um, each hidden neuron is connected to the each output neuron in the output layer. Okay, so the weight, the connection strength between the two neurons is represented in terms of the weights. So this weight matrix is called as Wij. I call it as Wij. That is the weight matrix between the input layer and hidden layer. Input layer and first hidden layer, that's called Wij. And the weight connected between the hidden layer J to the output layer K, I represent with the Wjk. Okay. So thus Wij, Wjk, we initialize randomly as we discussed in the earlier class. In addition to that, we have the bias parameters also. I said in the last class, bias parameters are for every neuron, we have one bias parameter except the input layer. At every neuron, we have the one bias parameter except the input layer. Okay. So anyone can tell me, I hope you understand what I'm saying. If that is the case, what are the number of model parameters in this ANN, number of model parameters MP, number of model parameters in the current ANN architecture? Anyone can tell number of model parameters? Any idea from the current
Four.
Number of model parameter in the current ANN architecture? Just sample architecture which I have considered for the demonstration purpose. So if this is the model architecture, ANN architecture, then total number of model parameters of this ANN architecture will be? So,
Four. Four.
not
Hello?
4, sir. Actually, so we have actually model parameters are nothing but the weights and biases. So if you come to the first part between the input layer and hidden layer, how many weights we have? There is a weight between the first neuron and first hidden neuron. First neuron, second hidden neuron. First neuron, third hidden neuron. First neuron, fourth hidden neuron. First neuron, fifth hidden neuron. Similarly, 2, 1, 2, 2, 2, 3, 2, 4. 3, 1, 3, 2, 3, 3, 3, 4. So what is the total number of weights between the input layer and output layer? That's equal to how many? So maybe W11, W12, W13, W14, W15, and W21, W22, W23, W24, W25, and W31, W32, W33, W34, and W35. So total number of weight parameters between input layer and hidden layer, that's equal to number of neurons in the input layer cross number of neurons in the hidden layer. Hope you agree. That means we have the 3 into 5, that's equal to 15 weight parameters between the input layer and hidden layer. Similarly, between the WJK. So WJK is nothing but the weight matrix between the hidden layer and output layer. So WJK equal to, that is the W11, W21, W31, and sorry, I can write here like this as a column matrix. So W11, W21, W31, W41, and W51. So this is the weight matrix between the hidden layer to the output layer. What is the shape of this one? That is the number of hidden neurons cross number of neurons in the output layer. That means 5 cross 1, that's equal to 5. So total number of model parameters are 5, 15 between the input layer and hidden layer, 5 between the hidden layer and output layer. Anything else? Any other model parameters we have for this current ANN model? Okay, it's okay. Then I will continuously. So what are the any other model parameters? I said that in addition, model parameters are the weight parameters and also bias parameters. And every neuron except the input layer, we have the bias parameter. That means there's a one bias parameter that is called BK at the output neuron. So one bias parameter at the output neuron, because in the output layer we have only one neuron. So one bias parameter at the output layer. And how many neurons in the hidden layer? 1, 2, 3, 4, 5. 5 neurons in the hidden layer. So that 5 bias parameters. 5 bias parameter means bias parameter 1, B1, B2, B3, B4, and B5. These all are the bias parameters for the hidden layer. B1, B2, B3, B4, and B5. For all the bias parameters, by default input equal to 1. So number of weights between the input layer and output hidden layer 15. Number of weights between the hidden layer and output layer is 5. Number of bias parameters in the output layer, that's equal to 1. And number of bias parameters in the hidden layer, that's equal to 5. So total number of model parameters of this ANN model equal to, so 26. 15 plus 5, 21, and 5, 26 model parameters are there. So during the training process, these 26 weights will be updated. These 26 weights will be updated during the training process. So these 26 weights will be updated such that for a given input x1, x2, x3, the model is able to predict the YP, which is almost close to your actual value. Almost close to your actual value. So if you participate actively in the session, it will be more interesting. And today's session is very important. Hope you will enjoy. I'm trying to give my best in today's session. Now, coming to, so now architecture is readily available. So now how the training process will be happened? How the training process will be happened in case of neural network, which contains the one hidden layer. Okay, which contains the one hidden layer. So, and one more thing I consider. So I want to use the linear activation function in the hidden layers. That linear activation function is sigma. So linear activation function in the hidden layer and also linear activation function in the output layer. Of course, most of the real-time problems are the highly non-linear, but first I'm trying to demonstrate with respect to the linear activation functions. Later we will move to the non-linear activation functions. So if you consider the linear activation function, there is a simply sigma term. So how the training process will be happened, we are going to discuss about the algorithm, and we will try to implement on using MATLAB and also using Python with a sample data. So in the last class, we discussed about the input layer and output layer with only weights, and later with input layer and output layer with bias also. Now we are increasing the complexity of the model by adding the hidden layer. With actually, we are using the linear activation function only, but with only linear activation functions, your model will not perform on on the complex problems, but only for easy of understanding. So I am explaining with the linear activation functions. Now, so if you understand what the session we discussed earlier, so if anyone responded, if anyone participated in the session actively, that will be more helpful. So if not possible, it's okay. I will continue, not an issue. So in the training algorithm, what will be the first step? Anyone can tell, please. What will be the first step in our training process of any neural network?
Read the data.
Yes, just read the data. So we have to read So read data. So read data is nothing but the X and Y read data. And we need to initialize our initialize learning rate
Values.
eta. And also you have to initialize how many number of iterations you want to run the training algorithm. And
Yeah.
later
Samples,
anything else we need to initialize?
weight and bias parameters. I
Yes.
think.
So we need to initialize the weights. Here we have the two weights. One is the weight between the input layer and J, that is the hidden layer. Another weight between the hidden layer and your output layer, K. And also we have to initialize, random initialize these two. So random initialize weights and bias parameter. Bias parameter is but the bias parameter at the hidden layer. And also we have to initialize the bias parameter at the output layer. So I think these are the things we are going to initialize. So before entering into the training process, that are the initial steps. So what next? So step 2. So that will be, so we have to start with the outer loop. That means we have to set iter equal to 1. And step 3. So that is you have to set sample equal to 1. Okay. Now step 4. So what we will do in the step 4, that is called forward pass. It is actually back propagation algorithm. Back propagation algorithm means in the forward propagation, we are going to calculate the output and error. And in the backward propagation, we are updating the model parameters. First, we will focusing on the forward propagation. Forward propagation in the step 4, that is the forward propagation. So what we will do in the forward propagation, we are going to calculate the output. We are going to predict the output, what ANN model is predicting, YP, we are going to calculate. So assume that we are using the linear activation function. See, any idea how we calculate the forward propagation output, YP, how we calculate the YP here? So if you want to calculate the YP, first you have to feed the input X, multiply with WJK, that will give the input to the hidden layer. Because I am using the linear activation function, same will be the output. And these outputs are passing through this WJK. That means you have to multiply with WJK. That will give the input to your output neuron. Where the output neuron, again, I am using the linear activation function. Your input is nothing but the output here also. So when you have the linear activation function, your input and output are equal for a neuron. But if you use the nonlinear activation function, that will be changes based on which type of nonlinear activation function we are using. Okay. So if that, I hope you understand. If that is the case, so how we calculate the first, if you want to calculate the YP, nothing but the predicted output of the ANN model. First of all, we have to calculate the output of the hidden layer. So output of the hidden layer we can calculate using OJ equal to, this is simply multiplication of your input with weight matrix Wij and add the bias parameters Bj. Right? That's what we are doing. So last class also we are discussing. So this is the input and multiply with the weight and add the bias parameters. That will give the input to the hidden neurons. But in the hidden neurons, we are using the linear activation function. Same will be the output. Same will be the output. Okay. So OJ value we are getting here. So once you got the OJ, next one, we have to calculate the YP. YP nothing but the output of the output neuron, nothing but the input of the output neuron. Because we are the output neuron, we are using the linear activation function. So what is the YP now? YP nothing but the predicted output of the neuron, predicted output of the ANN, which is coming at the output neuron. So YP equal to, you can see the architecture, YP equal to, that means YP, this one equal to, here we have the output of the hidden layer. And these output of the hidden layer passing through the WJK matrix. So what is the YP value? Output of the hidden layer multiplied by the weight matrix, add this bias parameter, then it will give the your output value for the output neuron. So YP can be calculated as, anyone please. So that is the OJ, that is the output of the hidden layer multiplied by the weight between the hidden layer and output layer plus the bias parameter at the output layer BK. That is the YP value we are getting. So this is a forward propagation is over. Forward propagation means just we are calculating the YP. Now step 5, that is called as the backward propagation. So backward propagation means we are going to update the backward propagation means, so we are going to update the weights and bias parameters. We are going to update the weights and bias parameters. So now if you want to update the weights and bias parameter, then we require the knowledge of back propagation, gradient descent algorithm. So based on the gradient descent algorithm, first we have to identify your objective function. What is the objective function? We are trying to minimize the square error, half square error. That half square error equal to 1/2 into your actual output value minus your predicted output value, that's whole square. Okay, that is whole square. Okay, y minus yp, that is a whole square. Okay, now so that's equal to, actually your yp is depending upon wjk, bk and oj. So oj is depending upon wij and bj. So indirectly your yp is a function of wjk, bk, wij and bj. So there are the four decision variables. We can call it as the model parameters. So these four variables will decide your error. So you are going to minimize the error means, so what you are going to do, you are going to update these four model parameters, wij, wjk and wbj and wbk, and add those to the old values. It will give the updation to the model parameters and decision variables. So first I want to calculate the delta wij, that means change in weights connected between the input layer and reading layer. So how we got this delta wij? So delta wij, how we got delta wij? So delta wij equal to, because delta wij is your decision variable. Like f of xy is a function of x and y, and how we calculate the delta x. So delta x equal to minus eta into dou f by dou x. Here also same thing. So delta wij equal to minus eta into dou e by dou wij. And similarly, how we calculate the wjk, that's equal to minus eta dou e by dou wjk. And how we calculate the delta bj, that's nothing but the minus eta dou e by dou bj. And how we calculate the delta bk, that's equal to minus eta dou e by dou bk. So we are going to calculate all the expressions and we will substitute in the step number 5. So first of all, we will mainly concentrate on is delta wjk and delta bj. First, we will concentrate on this one. Now see here. So this is the 1/2. So y minus yp. So yp is nothing but how we calculate the yp value. This is the yp value. Nothing but oj into wjk and minus bk whole square. And whereas oj again a function of wij and bj. That's why error is a function of wij, bj, wjk and bk. So first I want to calculate minus eta dou e by dou wjk. How we represent this one? I can write minus eta dou e by, I will represent wjk as dou e by dou yp and dou yp by dou wjk. So both are same, right? Dou e by dou wjk can be represented dou e by dou yp into dou yp by dou wjk. So that's equal to minus eta. What is the dou e by dou yp value? We are going to differentiate e with respect to yp. So it will become, this 2 comes forward and yp has a negative sign. So this will become say positive sign. So then this will become positive, and here we have the y minus yp, this term. And what about the dou yp by dou wjk? So what is the expression for yp? So dou yp. So yp can be calculated as oj into wjk plus bk, right? So when we differentiate yp with respect to wjk, so what is the value we are getting? That's
OJ.
equal to only oj. That's
OJ.
it. Thank you. So that is the oj. If someone is in fact will participating, that will be more interesting. But okay. So eta into y minus yp into oj. So that means you can calculate the delta wjk by using this formula and add this one to your old wjk, then it will be updated, right? So now I am substituting this expression in the back propagation step. In the back propagation step, how we update the wjk? So update the wjk, that's equal to wjk plus eta into y minus yp into oj. So this is the one updation of the wjk. Now second one, coming to the bk, delta bk. How we calculate the delta bk value? So delta bk equal to minus eta. So dou E by dou BK can be written as dou E by dou YP and dou YP by dou BK. So that's equal to, so dou E by dou YP, that means 2 come forward, minus sign is there, so it will become plus. So plus eta, and 2 come forward, 2 will be cancelled. So you have the Y minus YP and multiplied by dou Yp by dou Bk. Come here, dou Yp by dou Bk. So when you differentiate Yp with respect to Bk, we have only one. Only one. That's it. So just simply it is a 1. It's nothing but the eta into Y minus Yp. That's it. So now you can check here. So delta Bk. So Bk updation equal to Bk plus delta Bk equal to eta minus eta into Y minus Yp. So that is how we are updating the weights and bias parameters for the layer between the, for the region between the hidden layer and output layer, for the region between the hidden layer and output layer. Okay. So now what next? So we are updating the WJK. We updated the WBK also. Now our focus is we are moving to the other term. That means how we update the delta Wij. How we update the delta Wij. So how we update the delta Wij? So delta Wij can be updated as delta Wij equal to minus eta dou E by dou Wij, right? So that's equal to, so minus eta. So I want to rewrite this expression as dou E by dou Yp and dou Yp by dou Yp by dou Oj and dou Oj by what to have dou Oj by dou Wij. So you have the same expression, you can see. So Yp cancel, Oj cancel, then it will be dou E by dou Wij. Then eta into minus eta into dou E by dou Wij. Just I am writing like this, multiple partial derivatives. Then you can see what is the value of each. So that's equal to minus eta. So what is that dou E by dou Yp? We already discussed that previously. That Yp negative term comes forward, so it will become plus. The square term comes forward, we have the off term, 2 will be cancelled. So here we have the Y minus Yp. So this is over. And now what about the dou Yp by dou Oj? Dou Yp by dou Oj, we can consider now. So dou Yp by dou Oj, what is the Yp here is, and we are differentiating Yp with respect to Oj. Then what the value we have? What is the value we have? Yp by dou Oj. So that nothing but the Wjk. That is the Wjk. And what else we have again? So what we have again? So dou Yp by dou Oj over. Next dou Oj by dou Wij. So dou Oj by dou Wij means, so tell me what is the value? If you differentiate Oj with respect to Wij, then you have the value x. Then you have the value x. So this is the expression for delta Wij, that is the change in weights connected between the input layer and hidden layer. Now update the Wij expression. So the backward process, Wij is equal to Wij plus eta into what's called what is the value we have? Y minus Yp into Wjk into x, I think so. X, okay. So we'll check now. So eta into Y minus Yp Wjk, that's it. X, okay. And similarly, we need Bj. So Bj is equal to Bj plus delta Bj. And how we calculate the delta Bj? How we calculate the delta Bj now? So for the, I will give the derivation for the linear activation function only. We can do it for the non-linear also. We will see how we can manage that time. Otherwise, I will stop the derivation part for the non-linear activation function. Similar type of derivations. Procedure will be same, but the as we are using the non-linear activation function, the derivatives all will be changes, but the procedure will be remain same. So if you have interest, if you follow this video, this lecture, at home you can develop your own change in weights. with nonlinear activation functions. It's very interesting. Really, if you try, if you have interest, if you keep if you keep a note and pen and you sit, then you can practice. Then you will get everything. You can apply the same procedure, but for the nonlinear activation function. If the time permits, we will go that also. So coming to the delta Bj, so that can be calculated as minus eta into dou E by dou Bj. So how we represent this one? Minus eta into I will represent dou E by dou Bj as dou E by dou Yp, dou Yp by dou Oj, dou Oj by dou Bj. So that is nothing but dou E by dou Bj only. Then what we have? Dou E by dou Yp. We know about this one. It is a minus y minus yp. Already minus is there. It will become eta into y minus yp. And what is the dou yp by dou oj? Dou yp by dou oj. So see here. Dou yp, differentiate yp with respect to oj. So you have the wjk. So wjk. And dou oj differentiate with respect to bj. If you differentiate oj with respect to bj, if you differentiate oj with respect to bj, so we have the only one. Only one. That's nothing but the eta into y minus yp into wjk. That's it. Right? So this substitute here. So eta into y minus yp into wjk. Here we have the x, but here we don't have x. Here you have the oj, but here you don't have the oj. That's it. It is a backward propagation. There is a backward propagation. So weights will be updated. So what will be the next step? Now we are deriving all the expressions. That's why if you understand the basics of basic mathematics behind the neural networks, you can do more research work in the related to the AI. So coming to the step number 6. So now weights are updated. So what will be the next step, please? Anyone can tell? Step 6. The weights are updated. So now what will be the next step? So the weights are updated. That means what we are doing here, just we are passing the first sample. In the forward propagation, I'm calculating the output. In the backward propagation, I am updating the weights. So next step is we are going to update our sample. So sample equal to sample plus 1. That means if you are in the first sample, now we're going to the second sample. So what next? So step number 7. Step 7. So check for the whether if the current sample number is greater than total number of samples in the training data, yes or no, whether it is a true or false. Okay, that means if sample is greater than ns means all the samples in the data is covered. If not means all the samples are not covered. So if condition is true, then we are going to the next step. Go to next step. If it is a false, that means all the samples are not covered. Then we are going to which step? Go to step number. If all the samples are not covered, we are going to which step? Step number.
Iteration.
No, sir. Here all the samples are not covered. Let us do we have the 10 samples. Currently, we are in the second sample. First sample is completed, updating the weights, and we are going to second sample. So still 2 is not greater than ns, so it is a false condition. Then we are going to step number. We are going to step
Three.
number. We are going to step number 4. That means with the new sample,
4.
Again calculate the forward propagation output and backward propagation, update the weights. So we have to go to step number, I think it is 4. Go to step number 4. The forward propagation output calculation. So what's the next step? That means if all the samples are covered, let's assume, then what the next step? Go to next step. We said that go to next step. So what the next step? Step number 8. So what we are going to do here? Then we are going to update the iteration. Iter equal to iter plus 1. Again, in the step 9, we have to check for the convergence criteria, whether your current iteration is greater than max number of iterations you mentioned. So whether it is a true or false, we are going to check. So if it is a true, that means all the iterations, that means iter is greater than iter max. That means how many number of iterations you want to run the algorithm that already reached. So then go to next step. So if it is not, then go to, if it is a false, we are going to which step? The current iteration is not maximum iteration we are mentioned in the algorithm. Then we go to step number 3. We go to step number 3. Again start from the first sample. Go to step number 3 again, start from the first sample. So what next? So step 10. So step 10 is nothing but the simply calculate the errors. If the errors are not satisfied, if you are getting the large error, then you have to take some necessary actions. Like you may do some extra work on the data. You have to increase the data, variety of data, or you can change the model. You can tune the hyperparameters of your model. Like in case of the ANN, you may change number of hidden layers. You can increase the number of hidden neurons, or you can change activation functions. So like that, you have to tune the various hyperparameters of your ANN model. Still, if it's not working, then you move to some other new model, not ANN. Maybe some other model may perform well when compared to ANN. Then move to the some other model. So that thing you have to do if your performance of the model is not happy. Okay. So then suppose let us assume the errors are very less. If errors are very less, simply deploy your ANN model in application. So deploy your ANN model in application. So this is the complete training backpropagation algorithm for a artificial neural network. So I am explaining the derivation with a linear activation function with a single neuron. But the same thing, if you understand this concept, so you can take your book and pen, you can try for the different architectures if you have interest. But you don't want to know what is happening in the behind. You don't want to work in that direction. Only implementation. So for that one, this mathematics not required. Only if your task is only implementation of the ANN model, this mathematics is not required. But if you are the research scholar, you want to know the backend mathematics and you want to improve something, you want to build some new models, then you require this background, how models are working. So till now, I explained the complete algorithm. Now I am trying to write the code in the MATLAB on a sample data, and I want to show to you now. Okay. So coming to lab Python without hidden layer. So this completed without hidden layer, with hidden layer, with linear activation function, this part. So ANN with hidden layer and with linear activation function bias. And the data file is no bias. So, but we are adding the bias also with the hidden layer and with linear activation function, no bias. This one, no. So we are adding the bias parameter also. Yeah, this one. So ANN with hidden layer with linear activation function with bias. So I want to use sample data underscore 02. So I want to write this one code. Fine. So as usual, so we have to start with CLC and clear all. These two, nothing will do with the algorithm perspective, just it will clear the command window and workspace. So now what is our first task here? We have to read the data. So if you want to read the data, so file name equal to, so what is the file name? The data set file name that is available here. Sample something like 0 to this one. Just use that file name here. Just I want to use that file name here. Okay. And I want to read the data available in this Excel file into a variable in the MATLAB framework. So just I'm writing data equal to XLS read of file name. Just I'm reading the data, where in Python we are reading the read pd.read underscore Excel and pass that path. So it will read the data available in the Excel into the Python framework, but in the MATLAB environment. So just I want to save this code on the same space where my data is available. I want to give like ANN. So hidden layer and linear activation function. So that's it. So I want to build the algorithm, implement the algorithm in the MATLAB. So if you run this code, you are able to see the data file. For the data, it is importing onto the MATLAB to train your ANN model. Your ANN model contains the input layer 3, hidden layer 5. Sorry, number of neurons in the hidden layer. Sorry, input layer, number of neurons are 3. In the hidden layer, number of neurons are the 5. And in the output layer, number of neurons are the 1. Okay. Now coming to the data. So this is the data file. So once you import the data, so our next task is we are going to initialize all the required parameters. Just I'm taking the learning rate eta equal to 0.9. and I'm taking the number of maximum iterations that's equal to 100. Okay. So what next? Iter max, that's over, eta over. Now we are going to initialize what's called weight matrix and bias parameters. So that means we have the two weight matrix and two bias parameters. So Wij equal to, so first before that one, between on which range you want to generate the random weights. So I want to give the lower limit equal to -10 and upper limit that's equal to +10. Now you have to generate the random value, random weights. Wij equal to, that is the weight between the input layer and hidden layer, equal to, so lower limit plus rand multiplied by upper limit minus lower limit. Okay. So anything else we need to, anything additional change modification required in this line? Anyone can suggest, please. In the 10th line, do I need to do any modification? Any change is required in this code? Okay. So actually Wij shape is so Wij is the weights connected between the input layer and hidden layer. So number of neurons in the input layer equal to 3 and number of neurons in the hidden layer equal to 5. So you have to create a matrix with 3 rows and 5 columns. So this is how we generate the Wij. So now similarly you have to randomly initialize the Wjk as well. That means weights connected between the hidden layer and output layer. At least tell me what the change I have to incorporate in the 11th line. Or I can use the same for the Wjk random initialization.
5,1.
Yes, madam. Thank you. So it is a 5,1 because Wjk is the weight matrix between the hidden layer and output layer. Output layer has only 1 neuron, hidden layer has the 5 neurons. So it is a 5,1. Next. So coming to the Bj. So how? So tell me. So what the thing I have to what are the changes I have to incorporate to randomly generate the bias parameters for the hidden layer Bj. So Bj contains, so I'm trying to random initialize the bias parameters connected to the hidden layer. In the hidden layer, every neuron has one bias parameter. So in the hidden layer, we have the 5 neurons. So we have the 5 bias parameters. So that's why I want to rewrite this one as 5,1 because I have the 5 neurons in the hidden layer. And similarly, you have to initialize Bk. So Bk equal to, so Bk, so that's equal to, so this is the random initialization of the bias parameter in the output layer. So that's we can do here. We bias parameter correspond to the output layer. In the output layer, we have only one neuron, output neuron. So one Bk. So just one is deficient. You can use 1,1 or you can simply remove this one. Rand means single value is generated. So this is how our random weights and bias parameters are generated. And if you want to see those values, you can visualize in the command window also. Want to see those values, you can visualize. So Wij, what is the randomly generated Wij? This one. Randomly generated Wjk, this one. Randomly generated Bj, this one. Randomly generated Bk, this one. These are the random initialization. Later during the process, training process, all these parameters will be updated. All these parameters will be updated. Now initialization is completed. So now iteration starting, sample starting. So two for loops we are going to initialize. For iter equal to outer for loop is for the iteration, inner for loop for the samples. So iter equal to 1 colon iter max end and inner for loop for sample equal to what the data available here. I want to use the whole data for the training only, but generally out of complete data you have to use few percent of data for the training and remaining data for the testing. But here the sample I am using the whole data for the training purpose only. I'm not doing the data aspect. So here I am mainly focusing is how training was going to happen in ANN and how the predictions are doing. So sample equal to 1 colon number of samples. So how I extract the number of samples in the data? How I extract the number of samples in the data, how I get that information. Just I'm asking about the logic only. Is the data, I want to know number of samples in the data, how I can extract that one?
Number of rows.
Number of rows. So so we have to write the number of rows. Number of rows can be extracted by using the formula called command called size of your data matrix name, comma 1, that will give the number of rows. If you give the 2, that will give the columns. So close this for loop also. So in between, we have to write the complete algorithm. Here we have to write the complete algorithm. So in the for loop, first step is we are going to use the forward pass. So forward pass means we are going to calculate the YP. So if you want to calculate the YP, first we have to calculate the output of the hidden neuron, and later we have to calculate the output of the output neuron. So how we calculate the output of the hidden neuron? So already I demonstrated, we discussed already. So here, so forward pass, we have to write the two equations. One is the output of the hidden layer, another is the output of the output layer. So how we got the output of the hidden layer? The output of the hidden layer I am writing as the OJ. So OJ equal to X into W. So what is X? Not extracted. So first we have to extract the X nothing but input features in the sample. So X equal to data of sample. It may be one sample, second sample, third sample, whatever it may be, and the features. Is it right, or I have to change anything in the first 18th line? In the 18th line, do I need any modification is required? So in the 18th line, just actually I kept 1 to 4, but your input features are only 3. 1, 2, and 3
Yes.
columns only. So just keep the 3 here, not 4. So next, also extract your actual output, Y. So Y equal to, so where the actual output is available in the data, that is the sample, comma 4.
Fine.
That fourth column is your actual output. So this is the info. Now calculate the OJ. So OJ, as per this formula, OJ equal W X into Wij plus Bj. So X value X multiplied by Wij plus, actually X into Wij. This is the matrix called 1 cross 3, and this is the matrix called 3 cross 5. It will give the 1 cross 5. But Wj, we have to add the Wj, right? But Wj is 5 cross 1. So what we have to do here? You have to add the transpose of this one, otherwise it will throw a error. So that hyphen that represents the transpose. So you have to add the transpose. So once you got the OJ, next thing is we have to calculate the YP. So YP calculated as OJ into WJK, OJ into WJK plus BK. Okay. So YP equal to, what is the shape of OJ? That is the 1 cross 3, 3 cross 5. So it is the 1 cross 5. So you can keep OJ multiplied by WJK plus. So see, OJ is a 1 cross 5. It is a 5 cross 1. So when we multiply these to 1 cross 1, so you can directly add BK, no issue. But the single value. So now forward propagation is completed. So what next? Next one is the back propagation. Backward or back propagation. Next one is the back propagation. So in the back propagation, what we have to do now? We are going to update these parameters, right? We are going to update the weights, bias parameters. We are going to update. First, we update the WJK. So WJK equal to WJK plus. So what is the formula? Eta multiplied by Y minus YP multiplied by, that's it. WJK equal to eta into Y minus YP into what's called OJ. Actually, OJ matrix is so what is the OJ shape here? You can see OJ shape. OJ shape is it is 1 cross 3, 3 cross 5. So 1 cross 5. But WJK is 5 cross 1. So you have to do the transpose. You have to just you have to do the transpose or not transpose, that depending upon your matrix dimensions. Okay. So that's over. So next you have to do the BJ. So BJ equal to BJ. What is the, how we calculate the BJ value? So BJ value equal to BJ plus bj plus. So eta, you can see eta. So eta multiplied by. So what you have? Y minus yp. So you can call this y minus yp directly. That's it. Hope you understand. So we are updating the wjk and bj. Okay. Now in the coding, we have to do slight modification in the coding. Here, what it is doing here is, see, wij, nothing but the weights connected between the your input layer and the between the hidden layer, right? So here we are updating the weights one by one, not for all neurons at a time. We will take one hidden neuron and update the weights connected to the input layer, and take the second hidden neuron and update the weights connected to the input neuron. Take the third hidden neuron, update the weights connected to the that one. So this will be repeated for all the hidden neurons. Neuron by neuron, we are going to update. Okay. So for that one, so we have to initialize a what's called DWIJ, nothing but the delta WIJ. So we have to initialize zeros of how many. Actually, we have to add WIJ equal to WIJ plus delta WIJ, right? Actually, WIJ shape is 3 cross 5. So WIJ shape is 3 cross 5. So your delta WIJ shape should be 3 cross 5. So you have to initialize that one, 3 cross 5 zeros. Okay. So that's one first we have to do. When you are updating the WIJ matrix, which is a 3 cross 5 matrix, so your delta WIJ should be 3 cross 5. Then only we are going to add both. So, wait. So what I'm trying to do here is first initialize D, that means delta WIJ equal to zeros of 3 rows and 5 columns, because your WIJ shape also 3 rows and 5 columns. Okay. So next one is next what I'm doing is, so for I have to take the each hidden neuron. So j equal to 1 to 5. So you have to take the j equal to 1. Take the first hidden neuron, update the weights connected to that neuron. J equal to, take the second neuron, update the weights connected to that second neuron. J equal to 5, take the fifth neuron and update the weight connected to the fifth neuron. That process will be repeated. That's why I keep it in the while loop. Sorry, for loop inside. Okay. Now close this for loop. Now, first you have to calculate the change in weight corresponding to the first neuron. That means DWIJ, so colon corresponding to J. J means if J equal to 1, first neuron, first column update. J equal 2 means second neuron, second column update. J equal 3 means third neuron, third column should be update. So that's equal to, actually this is the IJ, I think IJ. So that's equal to, so how we calculate the delta Wij? So delta Wij is equal to eta into y minus yp into wjk. Wjk is nothing but the weight connected to that hidden neuron to the output neuron. That you have to add. So delta W is equal to eta multiplied by y minus yp. Sorry, y minus yp multiplied by what else? WJK. What is the WJK? WJK. Actually, in the WJK, we have the 5 values. 5 cross 1 matrix, 5 values, right? But which value you have to consider? We have to consider the weight which is connected to the first hidden neuron and corresponding output neuron, because when j equal to 1, you put j equal to second one, j equal to 3 third one, j equal to 4 fourth one, j equal to 5 fifth one. So that weight value you have to consider. So I will keep WJK of j. That's it. So that's how we are using the delta Wij, updating the delta Wij. Okay. At the similar, hope you understand what I'm saying. So once you find the delta Wij, now update the Wij. Wij equal to Wij plus delta Wij. So what next? So backward propagation, WJK updated, BJ updated, Wij updated. So what next we require? We need to update the Sorry, it is a BK kada. It is a BK, not BJ. See, you can see here. BK, this one is the BK. BK equal to BK plus 80 into Y minus YP. Okay, so it's a BK. BK equal to BK plus 80 into Y minus YP. Next, update the BJ. So BJ equal to BJ plus, for the formula, eta into Y minus YP multiplied by Y minus YP multiplied by WJK. Which one you have to take WJK? You have to consider the weight value which is connected to the corresponding hidden neuron and your output neuron. So that's why we are replacing the same here also. WJK of corresponding hidden neuron we have to consider. Okay. And here we have the X also. I think we forgot. We have the X value here, WJK. We have the X value here. Okay. So you have to keep X value. So multiplied by X is there now. So you have to represent X value here. So X transpose. You have to keep the X transpose. And you have to keep delta WIJ. I want to update DBJ. That means change in bias parameters connected to the change in bias parameter connected to the what's called hidden layer. That also I will initialize here. DBJ. So what is the DBJ shape? Actually, BJ shape. What is the BJ shape here? 5 cross 1. So our DBJ shape should be 5 cross 1. Because we are going to add both 5 cross 1. Now update the DBJ. So DBJ of J comma 1 is equal to, so what is the formula? Eta into this one. That's it. Now keep this DBJ and here. That's it. So this is how the weights and bias parameters will be updated. Now we will check for the one iteration. We will debug whether it is moving properly or not. Sorry. Yeah. So just I will keep the debugging point here. Just run the code. Now here we calculate the YP for the first sample, and the YP value we are getting this one something. Okay, and we are going to update the WJK. So weights are updated like this. Okay, weights are updated like this, and BK one value that also updated, and these two are the random initialized with zeros. Now first column, that means this first column is updated because first neuron weights are change in weight. This is the first neuron, the change in weights corresponding to the first neuron, and this one change in bias parameter corresponding to the first neuron. Okay, so like that we have to do it. That's it. So finally we have the delta B value something like this, and we have the DBJ values something like this, and now we are going to update the weight matrix. Now these are the weight matrix which is coming like this. Okay, so this process will be repeated for the 100 iterations, max. For the 100 iterations, it will be repeated. So I will remove this debugging point. Now you can run this code for the 100 epochs. So finally, you have the final weight matrix. So it is showing some weight larger. Do one thing, because of the larger learning rate, maybe it is showing the 9 values, undefined numbers. So now in this case, what you can do is try to reduce your learning rate. So I want to keep the learning rate as a 0.01 or 0.001. Then it may take a more number of iterations. Now we will see how the WIJ. Now it is the weights. So previously, when I'm using the eta equal to 0.9, so during the learning process, so the number becomes very large. So it's not printed on the command window. Then what I'm doing, so then I'm reducing the learning rate. then means the step size will be reduced. Then I am getting the stable weights. Okay, Wij, and you can choose the Wjk, and you can, these are the updated Bj value, and these are the updated Bk value. That's it. So this is how your algorithm will works. This is how your algorithm will works. So I will pause for the 1 minute. So if you have any question in this writing the algorithm or implementation of the algorithm using the MATLAB, and if you have any doubt up to here, please tell me. I will try to discuss with you. If you found any mistake, why you cancel this one, why you cancel that one, like that, please let me know. I will try to clarify your doubt. Just what we write in this whiteboard, same thing I am implementing here. So if you have any difficulty to understand, so please let me know. I will try to explain. Okay, fine. Okay, fine. So the weights are updated. The training process was completed. So once the training process is completed, what is our next task? So we are going to calculate the error. So we are going to calculate the mean square error. That means we have to calculate we have to pass the each sample to our ANN model, predict the output, calculate the square error, and add the all square errors of each sample and divided by the number of samples. That will give the mean square error. So we implemented that mean square error in the last class. I will use the same code. I will use the same code, but with small. So here I'm using the mean absolute error. Okay, I will use the mean absolute error. I'm using the same code, but a slight modification. If anyone suggests me where I do the modification, that will be more helpful. So if you not understand, please let me know. I will explain once again. So otherwise, at least give some suggestions from your end. So what are the modification of the code we have to incorporate here to calculate the mean absolute error? So no need of first line error equal to 0. We are initializing for loop, which is varying from the first sample to the last sample in the data. That's also no issue. This is also no issue. And this mean absolute is also fine. Only thing we need to do some modification here. Anyone can tell, please, what modification we have to incorporate in the 3 lines. While calculating the error, the model trained already. The model trained already. Now what we have to do here? First thing is X.
Data of sample of 1 gamma, 1 equal to 5, it should be.
So it is X value is already here also we have the 3 columns. So that's also fine. X value is fine. But this one prediction is nothing but simply what we are doing here. The same thing we can copy paste here. That's enough. What are the code is available in the forward pass? In the forward pass, what we are doing? Just simply calculating the output. Same code you can copy here. Because if you want to calculate the output, sorry, if you want to calculate the error, you have to calculate the output. So in the forward propagation, we are calculating the output, right? So I'm using the same code here. I'm using the same code here. So okay, so X equal to first 3 columns, that are the input feature. Y is the 4th column, that is the output variable. And Oj equal to X into Wij plus Bj transpose, and Yp predicted output equal to Oj into Wjk plus Bk, and finally error equal to error plus absolute value of, this is nothing but the Y minus Yp, just error, absolute error. Summation of absolute error divided by total number of samples, that will give the mean absolute error. So how we calculate the mean value? Pass the sample 1, calculate the Yp, calculate the difference Y minus Yp, that is called error. Pass the second sample, calculate the Yp, calculate the Y minus Yp, that is called error. And pass the third sample, calculate the Yp and calculate the Y minus Yp, that is the error for the third sample. So once we calculate the error for each sample and we want the mean absolute error, just sum all the absolute errors divided by total number of samples, that will give the mean absolute error. Hope you understand. So now I will run this code. I want to check what is the mean absolute error value, MEAE. So I am getting the mean absolute error at 1.2 1.2486. That is the mean absolute error. That's what I'm getting. Let's assume I'm happy with this error. So otherwise, so if you are not happy with this error, you can increase the number of iterations in the training process. So maybe it will give some better results. I will try to increase the 10,000 epochs. Iter max, I kept the 10,000 epochs, iter max. If suppose if you are not happy with 1.2486, then I will try to increase the number of iterations equal to 10,000. Now see what will be happen. Now you can see MAE. See, it's almost equal to 0. So these are the techniques we have to improve the performance of the model. Why it's happening? Because for a faster convergence, when I choose the learning rate equal to 0.9, then it throw an error, nan error. So nan error means not a number, it is very big numbers. Then what I am doing, I'm trying to reduce the learning rate to 0.001. But I'm not changing the iter max, it still I kept the iter max equal to 100 only. Because I am using the less learning rate value, it took the more number of iterations to converge. But my algorithm stopped at 100 iterations only. That means your solution not reaches to that bottom point. That's why we are getting the more error with iter max equal to 100. Then what I can do now, I increase the number of iterations to 10,000. Then then what happened? Because of the small step size, when the 10,000 iterations are reached, it reaches to this minimum point. So what I mean to tell you here is, so that type of idea or a logic or analysis that comes in your mind if you are able to understand the back-end mathematics. So what the thing here is, so actually in the first class I told, so it is like a objective function. Suppose if I choose the large learning rate, what happened for the faster? If you choose the large learning rate, it will come to the convergence point very fastly. But the problem is it threw an error called NAN, not a number, big number. Then what I'm doing, I am changing the learning rate to the 0.001. Because of the small learning rate, so my step size is very small, like this, like this, like this, like this. But I set the number of iterations to the 100 only. Then what happened? Maybe after 100 iterations, my update will be stopped here. That's why I got the more error. Then what I'm doing, I'm increasing the number of iterations to 10,000. Then it will take the remaining steps also. It will consider the remaining steps also. And finally, it reaches to this optimal point. That all happened. That is the reason why we are getting the error that's equal to the almost equal to 0. See, 4 into 10 to the minus 5 almost equal to 0. So why I can change these parameters easily? Because I understand what happened behind of the model. I have that idea. Because that one I'm changing those parameters. So now model is ready. So once the model is ready, what we are going to do? So model is ready. It was trained with the given data, and I set the I verified the errors, loss functions, loss values, and the loss value almost equal to 0, error value almost equal to 0. Now I'm happy, and my client also happy who will give the project to me. Now what is my next step?
Deployment.
Yes, deployment. So I want to deploy this model into an application. So this is an application code. So deploy my model into this application. So deployment of the model mean nothing but, what mean by the deployment? I will write application one more. Application underscore. Okay. So what mean by deployment? Deployment means
Calling them, like call that.
Just call the model. So call the model is nothing but just call the weights, stable weights. Just use stable weights into the application, and that application will use that ANN model in the form of the weights. Now, what are the weights we have actually? So I will remove all things. These are the related to some other data, some other model. So this is also not required. So call the weights. What are the weights we have? One is the BJ. So BJ value. So what are the BJ value here we're getting? Yeah, this is the BJ. So call this BJ matrix, bias parameters. So next BK. So what is the BK value? That's also available here. That value equal to minus 0 point or something we are getting. That's also we have to keep here. That's over. Next we have to call the weights between the input layer and hidden layer. So where that is available. Yeah, here Wij. So these are the weight matrix. You have to call that weights also. Enter. Next Wjk. That is the weights connected between the hidden layer and output layer. So you can use this also. So that's it. So I call the all the I keep all the weights and bias parameters into the application. That nothing but I am deploying my ANN model into this application. Now, what is the purpose of this application? It will ask the user about the inputs, and based on the inputs, able to predict the output. So it's calling the x1, it's asking x1 value, x2 value, and x3 value. So from these x1, x2, x3, you have to prepare a matrix x1, x2, x3. So what next? Based on these three inputs, we are going to predict the output. How we predict the output? So predict the output with nothing but a forward pass. So forward pass code you can directly copy here. That means you can forward pass code, these three we can directly copy here. Application. So x value is yp equal to w into x into b. No, sorry. Wrongly pasted, wrongly selected. Maybe where it is? This one. So what is the forward pass code? This is our forward pass code. OJ and YP. Just copy that code only here. Forward pass, in forward pass, we are calculating the predictions, right? That's it. Now simply it is the predict the output. So we will see. So we will check the data first. This one. So I want to use 0.1, 0.2, and 0.3. Expected value should be 3.6. So run this one. It is asking for the x1 0.1, 0.2, 0.3. So the value is 3.567. It's approximately equal to 3.6. The model is predicting well. That is the predicted value YP. That's how your application works. So just we are deploying the ANN model, nothing but the just hosting or taking complete trained weights and bias parameters into the application, and your application will use those weights for doing the prediction. That's what I'm doing here in the MATLAB. So hope you understand what happened in case of the artificial neural network, which contains the one input layer, one hidden layer, one output layer with linear activation functions, and explain the training algorithm, mathematics background, and implemented in the MATLAB. Okay. So as I said earlier, ANN model with a simple linear activation function, it may not work well. We have to go for the non-linear activation functions. We have to go with the non-linear activation functions. Okay. So if you consider the non-linear activation functions, how it will work, we are going to discuss now. It's very easy if you are able to understand this this thing. So I will explain with this one non-linear activation function, not all. So if you have interest, you can try at home with some other activation functions also if you have interest. But it requires some patience to do the calculations and to understand the process of weight and bias parameter updation. So now it is 3 o'clock. For the next 15 to 20 minutes, I am trying to demonstrate the ANN model with one input layer and one output layer, one hidden layer with the sigmoid activation function. With the sigmoid activation function. Okay. So yeah. So let us assume I want to construct a new architecture. So it's also some data like three input features x1, x2, and x3. It's going to predict the output variable y. Going to predict the output variable y. I will take only 15 to 20 minutes. Later we will go for the break. Coming after break, we will directly go to the Python implementation and MATLAB toolbox for the ANN implementation. Don't want to go for these type of mathematical demonstration and again writing the code from the scratch. So post break, we will try to focus on how we can implement the ANN model, how we can change the various parameters, uh, using the Keras deep learning framework. But for the first 20 minutes now, we will focusing on this ANN model with nonlinear activation functions. Okay. So again, I want to predict some variable y based on some input features x1, x2, and x3. So for this one, I don't want to implement from the scratch, but only I will try to explain the training algorithm. So this will help you to understand, to work with remaining nonlinear activation functions. Now tell me, I want to design a ANN model with one hidden layer. So one input layer and one output layer. So tell me number of neurons in the input layer. If this is the problem, so number of neurons in the input layer.
3.
3. So number of neurons in input layer, that's equal to 3. So each neuron will catch the information from the each input feature x1, x2, and x3. And we have the only y prediction. So we have the only one neuron in the output side. So that will give the predicted output yp. In between, I want to take only single hidden layer. So with 5 neurons, I am considering. So it is a random. You can choose any. So you have to tune the number of neurons in the hidden layer. So now, so these are the weights connected between the first input neuron and the remaining all hidden neurons. And similarly, second input neuron with hidden neurons, and the third one and with the hidden neurons. And similarly, output, input and output, hidden and output, hidden and output, and hidden and output. So between the input layer and the hidden layer, we have the weight matrix that is called Wij, and here Wjk, and assume input layer represented as I, output layer, hidden layer represented with J, output layer represented with K. And every neuron in the hidden layer has one bias parameter. So it's the B1, B2, B3, B4, B5. For all the hidden bias parameter, the input is 1. And we have the one output neuron. So we have the one bias parameter, the output neuron, that is called BK, let's assume. So these all represent the BJ. This is what same. So what the thing additional here we are doing is, instead of using the linear activation function, I am using the sigmoid activation function in all the hidden neurons. In all the hidden neurons, I am using the sigmoid activation function. So we model a sigmoid activation function. Maybe in the second class, Vinod Kumar sir will explain. I think he was explained about the various activation functions. So sigmoid activation function is represented as f of x equal to 1 by 1 plus e power minus x, where x is called as the input to your sigmoid activation function. X is called as the input to your sigmoid activation function. Okay. So now we will work on the training algorithm. So now we will work on the training algorithm and require derivations. And one more thing I want to tell, if f of x, that is called sigmoid activation function, f of x equal to 1 by 1 plus e power minus x, then it's a derivative. F dash of x is equal to f of x into 1 minus f of x. So if you have any doubt, you can try to differentiate this f of x with respect to x. You will get this expression only. But we have a time constraint. I don't want to go for this derivation. Okay, you have to remember this one. So derivative of the sigmoid active function equal to f of x into 1 minus f of x. Okay. So because this is required, that's why I am mentioning here. Now coming to the training procedure. So step 1, as usual, read the data. So that is the x and y, and initialize your eta, learning rate, iter max number of iterations, and also random initialize Wij matrix, Wjk matrix, and Bj matrix, and Bk matrix. Okay. And step 2. So step 2, what is the step 2? You have to start with iteration 1, and step 3, you have to start with sample 1. Now tell me step 4. What is the step 4? For the step 4?
Weights.
Weights are already initialized, Wij, Wjk, Bj, and Bk. So step 4 will be forward pass, forward propagation. So forward pass. The forward pass means what we are going to do in the forward pass, we are going to calculate the YP. So if you want to calculate the YP, predicted output, so what we have to do, calculate first, you have to calculate the input to the hidden layer, and later you have to calculate the output of the hidden layer. In this case, your input is output not same. Because in the last architecture, we consider the linear activation function, your input and output is same. But here I am using segment activation function. If your input is x, then your output is 1 by 1 plus e power minus x. You have to remember. So first you have to calculate the net input to the hidden layer. Later you have to calculate the output of the hidden layer. And with this output passing through the WJK matrix, calculate the input to the output layer. Again, here also we are using the segment activation function. Now you have to calculate the output of the hidden layer, sorry, output layer. So those things we have to calculate. Output of the output layer, output here is nothing but the YP. So these things we have to do in the forward propagation. Slightly complex. See, the complexity is increasing for the model. So first we have to calculate the net input to the J, that means hidden layer. So net input to the hidden layer, how we calculate net input to the hidden layer? So net input to the hidden layer, how we can calculate the net input to the hidden layer? That nothing but the your inputs multiplied by your weights, add this bias parameters. Okay. So net input to the hidden layer equal to your x into wij plus add your bias parameters of the hidden layer. So once you got the net j, that means input to the hidden layer. Now calculate the output of the hidden layer. So how we calculate the output of the hidden layer? How we calculate the output of the hidden layer? Because we are using the sigmoid activation function. So for the input layer, the net input is net j. Then what is the output of the hidden layer which having the sigmoid activation function? So Oj equal to 1 divided by 1 plus e power minus net j. E power minus net j. Okay. And similarly, once you calculate the Oj output of the hidden layer, now calculate the net input to the output layer. Net input to the output layer. How we calculate the net input to the output layer? Anyone can tell, please? Net input to the output layer. So net input to the output layer is nothing but the so this one. Net input to the output layer, I'm telling. So we have the outputs of the hidden layer. We have the outputs of the hidden layer. And these outputs are passing through the WJK matrix. So
WKT.
yes, madam. Thank you. Thank you for the response. So we have the OJ into WJK. Anything else? Plus we have to add the bias parameter BK. And later we have to calculate the YP, nothing but the output of the output neuron or output of the output layer, nothing but OK, nothing but YP. So YP equal to, again, we are in the segment activation function. So 1 plus e power minus net K. Because I'm using the segment activation function, I'm taking this one. Suppose in the output layer, if I using the linear activation function, what is the output? Here, YP equal to 1 by 1 plus e power minus net K, because in the output layer, I consider the segment activation function. Instead of segment activation function, if I consider the linear activation function in the output layer, then what is the YP value? So if I am using in the output layer, in this architecture, I consider the segment activation function in the output layer. That's why I'm considering the 1 by 1 plus e power minus net K. Instead of segment activation function, suppose if I use the linear activation function only, I'm using the segment activation function in the hidden layer, but in the output layer, I consider only linear activation function. If I consider linear activation function, then what is the YP? So if we consider the linear activation function for any neuron, if you consider the linear activation function, what the input to your linear activation function, same will be the output. So that means your net K itself it is a YP in case of linear activation function. But here we consider the segment activation function, then YP and net K both are different, and YP equal to 1 by 1 plus e power minus net K, because I'm using segment activation function. So we have the YP value. We have the YP value. Once we have the YP value, that means prediction is completed, forward process closed. So we are predicting the output, we are calculating the output. So forward process is closed. If the forward process is closed, so what is the next step? Step 5. So step 5 is nothing but so step 5 is the backward pass. So backward pass, when the backward pass, the weights are going to update. The backward pass weights are going to update. Okay. So that means we have to calculate Wij equal to Wij plus delta Wij and Wjk equal to Wjk plus delta Wjk and Bj equal to Bj plus delta Bj and Bk equal to Bk plus delta Bk. So now our main intention is we are going to calculate the delta Wij, delta Wjk, delta Wbj and delta Bk. So these things are required. So for that we require a mathematics again. Gradient. So how we calculate the step length? That for that we require again gradient descent knowledge is required for you. So once you calculate the Yp value, now calculate the E value. So E equal to 1 by 2 into Y minus Yp whole square. Now, if you want to calculate the delta Wjk, first focus here. If you want to calculate the delta Wjk, how we calculate the delta Wjk? That's equal to minus eta into dou E by dou Wjk. Dou E by dou Wjk. So that's equal to minus eta into. So dou E by dou Wjk can be written as dou E by dou Yp and dou Yp by dou Wjk. Now what is the value here? Minus eta into what is the dou E by dou Yp? Here minus n is there, it will become plus, and square term is there, come forward, 2 will be cancelled. So you have the y minus Yp. And what about the dou Yp by dou Wjk? How? Still, see, Yp is not direct function of the Wjk, but it's the direct function of net k. So I want to again split this derivative as dou Yp by dou net k and dou net k by dou Wjk. Then both are same. Now tell me what is the dou Yp by dou net k. Yp nothing but this one. This is the input net k. Now what is this called sigmoid activation function? This is a sigmoid activation function. Now what is the derivative of this sigmoid activation function? Just now I told, but we don't want to derive again. It will take time. Not it will take some time, but already I gave. So the derivative of sigmoid activation function f dash of x equal to f of x into 1 minus f of x. Right? Yeah. So here your sigmoid is Yp, right? So your d dou Yp by dou net k nothing but the Yp into 1 minus Yp and dou net k by dou Wjk. Here, this is the net k, this is the Wjk, and this is the Oj. So what is the dou net k by dou Wjk? That value equal to Oj. Perfect. So just this is the formula you have to incorporate here. Later, you can code it based on this requirement. You can code it either in the MATLAB or in the Python, whatever it may be, you can write. But Python is more familiar because we have the libraries, more libraries. So what is the this one? So not this one. Sorry, is the Wjk, right? Wjk. So Wjk means we have to replace here. So Wjk, that's a delta Wjk, that's equal to eta into y minus Yp into 1 minus Yp into Oj. That's all. Now, any idea based on since yesterday, that means day before yesterday class, we discussed about all these type of derivations and we are applying the knowledge of gradient descent algorithm for the weight updation. Now, anyone can tell what may be the proper delta Bk expression from this, what may be the proper delta Bk expression? Otherwise, I will explain again. So delta Bk can be written as so minus eta into dou E by madam.
No, sir.
Okay, dou E by dou Bk. So this can be further written as minus eta dou E by dou Yp, dou Yp by dou net k, and dou net k by dou Bk. So this one is represented with three products of the three partial derivatives. Then what is the value? So dou E by dou Yp, dou E by dou Yp, dou E by dou Yp. So you have the minus sign. So this will become plus. Dou E by dou Yp means square term comes forward, 2 will be cancelled. So the dou E by dou Yp expression can be written as eta into y minus Yp What is the dou yp by dou net k? Already we calculated here. Dou yp by dou net k. So dou yp by dou net k means this one. So yp into 1 minus yp. So again it is a yp into 1 minus yp. And new thing is dou net k by dou bk. So what is the dou net k? You can see. Net k value is this one. And dou net k by dou bk. Differentiate net k with respect to bk. Then you have the dou net k. Differentiate with bk. That value is 1. So that means here we have the 1 into 1. That's it. Into 1. That's it. So finally, you can replace this bk expression as with eta into y minus yp into 1 minus yp. So once the mathematics, you are good in mathematics, you can apply same concept with any programming. But you have to know first what the expressions are there for the change in weights and the change in bias parameters. Fine. So we have delta wjk updation is over. WJK updation is over and BK updation is over. So next one is delta Wij. I want to concentrate on delta Wij. Okay. So how we update the delta Wij now? You can see. So delta Wij is equal to minus eta dou E by dou Wij. Okay. So this can be written as minus eta. Actually, E is not direct function of Wij. E is direct function of Yp. So I can write dou E by dou Yp. Dou Yp is a function of net k, dou net k. And dou net k is a function of Oj, dou Oj. And dou Oj is a function of C. I'm unable to recollect. Oj is a function of, Oj is a function of net j. So Oj is a function of net j. Dou Oj by dou net j. Again, dou net j is a function of you can see. Dou net j is a function of Wij. Okay, so that you have to is a function of Wij. Dou Wij. Now you can see the simple dou E by dou Wij partial differentiator. I want to keep it as a product of all these 5 partial differentiations. This thing. Now you can see what is the value. So what is the value you can see. So dou E by dou Yp into minus eta. That value equal to eta into y minus Yp. We discussed it till now. What is the dou Yp by dou net k? You can see. Somewhere we have right. Dou Yp by dou net k. That is the Yp into 1 minus Yp. Yp into 1 minus Yp. Next, dou net k by dou Oj. Dou net k with respect to Oj. We have the dou net k expression somewhere. Yeah. Dou net k with respect to dou Oj. Then we have the Wjk. We have the Wjk. Next, dou Oj by dou net j. See the Oj expression. Now tell me at least what is the dou Oj by dou net j? Concentrate here. What is the dou Oj by dou net j? Dou Oj, differentiate Oj with respect to net j. Because it is a sigmoid activation function, right? Sigmoid activation function like f of x equal to 1 by 1 plus e power minus x. It is a sigmoid activation function. For a sigmoid activation function, what is the f dash of x? It is the f of x into 1 minus f of x. So what is the Oj dash? That means dou Oj by dou net j. Is nothing but Oj into 1 minus Oj. And finally, we have the dou net j by dou Wij. Dou net j by dou Wij. So dou net j, differentiate this one with respect to Wij. So you have the x. That x value I am writing here. So this is your final delta ij expression. Delta wij expression. Just substitute this whole part here. Delta w eta into y minus yp into 1 minus yp into w jk into oj into 1 minus oj into x. That's how we are going to update the wij matrix. Same formula we can same procedure we can apply for the bj matrix also. Then your delta bj will have this x will not come into picture, remaining all same. This x will not come into picture in case of the delta bj. So then we have the eta into y minus yp into 1 minus yp and wjk into oj into 1 minus oj into x. Sorry, no x, sorry. So because we are differentiating with respect to bj, na? So bj don't have a coefficient, it has a coefficient 1 only. That's why into 1. So this is how we are going to update the weights in the step number 5. To update the weights and bias parameters connected between the input layer, hidden layer, and output layer. So rest only step 5 and step 4 change. Remaining all are same. So what will be the step number 6? So step 6, we are passing the first sample. We are passing the first sample. Forward pass, calculating the YP. Backward pass, updating the weights. So what next? Step 6. What will be the step 6?
Update sample.
Yes, update the sample number. So sample equal to sample plus 1. And step number 7. So that's equal to check for the sample. If the current sample number is greater than the number of samples or not. If it is a true, where to go? If it is a false, it is where to go. If the current sample number greater than the number of samples, that means all samples are covered. Then go to next step. So if not covered, that means all samples are not covered available in the data set. Then where to go now? Which step you have to go?
Step 3.
If all the step number
3.
So if you go for the step number 3, again it starts from the sample 1 only. So first we are passing the first sample. In the next step, we are calculating the YP. Next step, we are updating the weights. Next, increasing the sample number. Now we are going to sample 2. So that sample, let us in our data, we have the 10 samples. Now we are in the second sample. That means all samples are not covered. Then with the second sample, what we are going to do?
Okay, yeah, forward. Go
forward.
to step
That
4.
means we are going to the step number 4. So we are going to the step number 4. We are going to the step number 4. So if it is a true, go to next step. Next step means step number 8. What we are going to do? Step number 8. Update the iteration. Iter equal to iter plus 1. And step number 9. These all are same again. Only step number 4 and step number 5 is changes. That depending upon the architecture. Step number 9. Now check for the number of iterations. If iter value is greater than iter max or not. So if it is a true, if it is a false. If it is a true, go to next step as usual. If it is a false, if the current iteration, let's assume we are giving the number of iterations equal to 100. Now we are in the second iteration. Iter equal to iter plus 1 means we are going to the second iteration. So that means it is not 100, it is less than 100. That means all number of iterations not executed. Then where to go? False.
Step 3, sample 1.
Step 3, yes, sir. So we have to go to the step 3, again start with the first sample. Go to the step 3, again start with the first sample. So this is about the step 9. And finally, let us assume if it is true. That means all iterations what you mentioned in the algorithm is happy. Then you can simply calculate the error.
Error condition.
Error calculation. So see in the last class, in the previous demonstration also, initially I set the eta value as a 0.001 and set the iter max equal to 100 and executed the code. I got the error around 1.2. Then I was not happy. Then what I did, I increased the number of iterations to the 100 iterations. Then again retrain the model. Then I got the error equal to 0. Like that here also, check the error, calculate the error. If you are happy with this one, then it's fine. If you are happy, then go to deploy model in application. Okay. If that is not the case, if the errors are not satisfied, then you have to redo it. What are the things that in your hand? Maybe you can change the learning rate. Maybe you can change the number of iterations. Maybe you can improve the data, or maybe you can change the hyperparameters of your model, like number of hidden layers, number of hidden neurons, activation functions, optimizer, and all the stuff you have to do. Still, whatever things in your hand, everything not working fine, anything not working fine, then what you can do is you change your model. That's the only final option. Suppose if you have one person, one student we have with us, we give our best, what we want, we can give everything to him. If he's not accepting anything, if he's not changing at all, then what we will do? We will go for some other person. That's it. Here also, I took some ANN model, I tried what I can do, but not performing well at all. Then I can go for some other model. That's the final option. So this is all about the model algorithm of the artificial neural network model, with one hidden layer, one input layer, and one output layer with the nonlinear activation functions. Okay, but we have a time constraint, so I don't want to. Actually, all the codes are available. I shared one GitHub link with you. In that GitHub link, you have that Python notebook, and you also have a MATLAB code files. So whenever you have a time, you have some interest, so try to work on those codes and with those data sets. So if you have any queries, if you have any doubts, you can feel free to text me. If I have free, I can respond back after seeing that message. So that's why I don't want to implement this code from the scratch. So what we did till now, I don't want to explain this one. I'm trying to move on to the Python and MATLAB implementations using Keras deep learning framework, and also using MATLAB toolbox. So maybe some it may be helpful for you to work on projects. If you want, you can take a only 5 minutes break, please. So we don't have much time. That's why. So now it is around 3:30. So we will take a break up to 3:35, and we will start the second session of last day, day 5, at 3:35. And meanwhile, if you have any doubt, if you have any questions, you can ask.
So this GitHub, Canvas, and these YouTube links will be active, right, for some more time? Or?
It's already active, sir.
No, for some more time, like for another week or
Okay,
10 days,
that's
it will
that's not